the command and control of nuclear weapons. Now imagine the US president is woken up in the middle of the night and told by his military aide there are 3 missiles that look like they've been launched from the Atlantic and they're flying towards Washington. What do we do? The missiles will be here in about 15 minutes. A universal consideration of nuclear command and control is the degradation of the electromagnetic spectrum because it affects communications and sensors. When you take a rock and you throw it into a lake and you see the waves that spread across the surface of the water, nuclear weapons can spread waves that obscure visibility, that make it difficult for radars to see incoming targets. Nuclear detonations at all altitudes can cause some communications degradation. However, nuclear detonations at 70 to 100,000 feet, which is about 21,500 meters, cause severe electromagnetic effects. An EMP would result if, for example, gamma rays hit the atmosphere. And beta particles in gamma rays would warp radio waves, especially in the high frequency range. These EMP effects could last for several hours, whereas a surface or low airburst would not have the same effect. This would disrupt most communications and electronics. Very long wave and very low frequency communications tend to resist electromagnetic disturbances the best, and that's why they're used to communicate with submarines. But the rate of communication is very slow. Here you can see the wavelengths in centimeters. The aircraft here is a US Air Force NATO E-3A AWACS Sentry. The pizza on the back is basically a radar radome that tracks aircraft and other flying objects. Here you can see the effects of nuclear detonations on different elements of that electromagnetic spectrum. The central column describes the distance and the length of disruption. So VLF, very low frequency, can be disrupted for hours and for thousands of miles. And UHF on the bottom is effective for just a few tens of miles and seconds to a few minutes. So a major problem is, because of the effect of nuclear radiation bursts have on the electromagnetic spectrum, it's very difficult to conduct BDA, battle damage assessment, and find out what effect did the nuclear attack actually have on the target. Did the missile never make it? Did it arrive but miss and only damage the target partially? Or was the target destroyed? And if I'm going to fire a second volley, am I simply wasting nuclear weapons on a target already destroyed? The typical solution after initial strike is to conduct multiple follow-on bomber attacks to make sure the targets are finished. Dust from nuclear war in the first few days would affect strategic surveillance by satellites of launches and incoming missiles by radars. Radars focused on early warning and, for example, non-nuclear interception, such as interception of aircraft. And it would also disrupt laser beams for communications between ships, and interception from ground-based missiles would probably be ineffective if there was too much dust. Once strategic command facilities are destroyed, it will be virtually impossible to direct the tactical nuclear war from the center, and it would probably have to be decentralized to tactical nuclear forces that are fighting. Here you can see at the very bottom right the Spartan missile farm. These were missiles as a part of the US missile defense. We'll talk about this in a later lecture. So you have an incoming missile and it detonates above the radar, and this creates behind it a blackout. Basically an area where missiles can come in and it's not visible to the phased array radar. That's the PAR you see at the bottom. A phased array radar is actually not a big radar, but many small radars that can be redirected by a computer. And so it provides much more accurate resolution of the number and types of targets. And it also allows the radar to track a great many targets at the same time. So let's take a look at one command system, which we know about because the end of the Cold War allowed us to get some access by Russian scholars at how the Soviet Union did their planning. And so peculiarly, we have more knowledge of how the Soviets conducted their nuclear command and control than we do about how the US does their command and control. So the Soviet and Russian command and control. The President of Russia has nearly the identical overarching control of nuclear weapons as the General Secretary of the Central Committee of the Soviet Union. Subordinate to him is the Defense Council, consisting of senior civilian and military representatives, and this becomes the Supreme High Command in time of war. In peacetime, Russian nuclear forces are under the command of the General Staff. These include the Strategic Rocket Forces, which is responsible for all strategic missiles and has 100,000 soldiers. The naval forces that command the ballistic missile submarines, the air forces that command the strategic bomber forces, and the ground forces which command theater and tactical nuclear weapons, mostly theater missiles. The main operations directorate of the General Staff prepares the equivalent of the Russian PSYOP with its list of options. You can see here the C3I setup of the Soviet Union. This architecture consists of different echelons of non-nuclear leadership, satellite communication centers, and assorted telecommunication centers, and other surveillance. C3I stands for Command, Control, and Communications and Intelligence. The Soviets had three operational scenarios. 1. The preemptive or first strike. This was reserved for the anticipation of an attack or an ongoing attack on command and control facilities in anticipation of a full-scale assault. In other words, the Soviets were well aware that the US had a doctrine of targeting communist leadership as a part of their decapitation attack. Scenario 2. The counter-strike of launch on warning. Launch on warning, or LUA, launch under attack as the US calls it, is when you launch your missiles in the silos after you detect the enemy's missiles coming in, and you try to get your missiles launched and away before the enemy's missiles hit your silos. This is the principal task for which Soviet and Russian strategic forces trained. No surprise, it's exactly the same thing that the US spent most of its time training for. Scenario 3. The retaliatory or second strike. This relies on less accurate forces such as sea-launched ballistic missiles. Under routine conditions, it is impossible to launch a nuclear attack. In this mode, the command links are disconnected, making authorization code transmission for attack impossible. The command link is engaged during crises or attacks. For example, bombers, units on combat duty are not ready for takeoff or armed with nuclear weapons unless there's a crisis alert status. When an alert status has been declared, road and rail mobile systems are dispersed. Ballistic missile submarines are sent to sea, and bombers are loaded and sent to dispersal airfields. The communications with Soviet submarines is by very long wave radio. This can penetrate water to 5 meters, and so the submarines have to rise to periscope depth or use towed antenna for instructions. 5 fixed Soviet-era transmission stations in the range of 3 to 30 kilohertz transmit every day. Mobile land-based and aircraft-based very low wave communication systems were established with 13 aircraft of the type Tupolev 142 maritime reconnaissance. 7 were deployed in the Pacific and 6 in the Atlantic. Very low frequency of a few dozen hertz can penetrate between 200 to 300 meters of water. The Zevs VLF station in the Kola Peninsula in the Arctic can contact a Soviet submarine anywhere in the world. The rate of transmission is very slow. Soviet submarines that do not respond or send outgoing communications. The situation normal code is sent at regular intervals. The lack of this code is the first step in an emergency. Soviet submarines could not launch without authorization codes. Rail and airborne command posts are deployed in times of crisis. The Central Command Reserve Headquarters is at Yamantau Mountain, and this would be activated. Moscow has an underground train that's 10 kilometers long and brings the Soviet leadership to Remenki, which is a bunker complex, and can also take them to Kuibyshev. This is a comparison between the US and Soviet peacetime versus crisis readiness. US ICBMs are 95% alert at all times, peacetime and wartime. Ballistic submarines are 67% in peacetime, but in a crisis, somewhat more would be deployed. No US bombers are ready during peacetime, and 50% are deployed in crises. In Russia, the alert status deployment is much lower. In peacetime, only half of the ICBMs are alert. In a crisis, that only goes to 80%. Less than half of the ballistic missile submarines are deployed in peacetime, about 2/3 during a crisis. And in modern times, post-Cold War, the peacetime deployment of Russian ballistic missile submarines is actually lower than 44%. The Soviets have the same bomber deployment level as the US. Soviet ground-based early warning systems can detect incoming ICBMs and sea-launched ballistic missiles. The Early Warning Command Center attempts to confirm the signal, unless the number of incoming missiles exceeds a certain number. There are actually a number of cases where Soviet radar operators were confronted with an apparent attack and then discovered it was an anomaly, a training tape, or they were detecting something in nature. And in all of these cases, the Soviet operators, being skilled, made the correct diagnostic of the actual situation. So these types of false positives occur all the time, and it's the importance of the training of these individuals to make sure there isn't generated an accidental false alarm that could start a nuclear war. The missile attack signal is transmitted from the Early Warning Command Center to the Central Air Defense Command, the PVO, and the Central Command Post of the General Staff, who then confirm the validity of the signal. If the attack is detected by the space-based early warning system, then the missile attack signal is automatically transmitted to the Kazbek terminals with the President. The Kazbek terminal is a system of communication that is carried around near the President. Also, the Kazbek terminal with the Ministry of Defense and the Chief of the General Staff, who have their own Kazbek terminals, and automatically alerts the battle management staffs into combat mode. Now, the actual vehicle through which you communicate through the Kazbek terminal is the Cheget Nuclear Command briefcase. And this was possessed by the national leader, the Minister of Defense, and also the head of the General Staff. Russia's BMUS system, which is their ground-based anti-missile surveillance radars, is operated by the 3rd Separate Early Warning Army of the Missile Space Defense Forces. Russian radars can detect an incoming warhead at about 6,000 kilometers distance and an altitude of 3,000 kilometers, which means they're exo-atmospheric, or outside the atmosphere. One of its major issues is having to rebuild a new radar, as former Soviet states are basically trying to have Russian radars removed from their territory. So a lot of the Soviet-era radars were in Kazakhstan and Uzbekistan and Belarus and the Ukraine. The Russians also rely on space-based surveillance for boost phase launch detection. We will talk about missile defense later. Boost phase means the rocket is rising slowly because it's trying to take off and go into space, and typically rockets go quite slowly, and because of the fact that it's just ignited its fuel, there's a giant hot plume of smoke or fire that's basically projecting it upward. So it's relatively easy to detect. This is the Soviet integrated surveillance of the US. It includes radars that bounce off the exterior of the atmosphere and allow detection of missiles launched over the Arctic. It also includes satellite surveillance. So those are the OTH, or the over-the-horizon radars that are ground-based. The Soviet Union also operated, and the Russians do as well today, early warning space-based satellites that sweep over the US in a regular pattern. And some of them are geosynchronous, which means they hover over the US for long periods. These are the Soviet-era radar surveillance coverage. You can see here the Dnepr and the Dnestr M radars. These are changes to the radar surveillance architecture introduced by Russia after the end of the Cold War. You can see the very powerful radars emanating from Moscow for their missile defense system. These are graphics of assorted Soviet radar sites. After having received the missile attack signal, the highest command authority, the president or his delegate, would decide on whether to give the preliminary command to either the central command of the General Staff to link up the battle management system necessary to transmit the launch codes. The president transmits his authorization through the Cheget briefcase to the Kazbek launch computer terminal. The president could also transmit the order to execute one of the attack options. One of the fail-safes in the Soviet system was that it was impossible for the supreme authority, the president, to command a preemptive or first missile launch without a missile attack signal being transmitted from the early warning system. So the Soviets were concerned that they might try, or someone in the process might try, and do a preemptive strike. So they had this guard against that. The US does not have this limitation. The Soviet leadership was thus vulnerable to a decapitation attack from executing a launch on warning attack. So if the US launched missiles, and the Soviets detected the missiles, if the US could destroy the bunker before the Soviets could generate the command, or before they detected the incoming US missiles, then they wouldn't be able to send out the launch code. And the Soviet missiles in the silos would probably be severely attrited. It remains to be seen if the Russians have changed this vulnerability. The General Staff Central Command would then execute the presidential order through its redundant network to all subordinate forces called upon in the strategic plan. The missile attack would have to be generated manually by the General Staff. All of this would take place in a matter of minutes. In the event of a failure of a launch on warning because of decapitation, the General Staff could still issue a command to link up and launch command on its own in the following circumstances. 1. They can confirm the absence of communications with the Supreme Commander. For example, the President has been killed in the Kremlin. 2. Seismic sensors must have picked up nuclear detonations on the surface in Russia. The US has a similar system called the bomb alarm. Number 3. The Supreme Commander must have delegated permission for a retaliatory attack. This would release it to use a second set of command codes for a launch order. One of the reserve systems available to transmit the launch order was the perimeter system. This consisted of missiles launched continuously transmitting the launch codes for 20 to 50 minutes. And this bypassed the missile command post and permitted individual silos to launch their rockets. The United States Command and Control System. The AFSBC, the Air Force Space Command, is deployed at Peterson Air Force Base, Colorado. It provides ballistic missile warning, space control, worldwide satellite operations, and it maintains the ICBM force. In the early 1970s, the U.S. parked 3 geosynchronous satellites over the ICBM fields in the USSR. Geosynchronous means it's always hovering above the same location in the Earth. Geosynchronous satellites have to be in deep space. If they're too close, they're going to fall through the atmosphere and crash. Warnings would be sent directly to the Pentagon without the NORAD initially. There were 3 DSP satellites for surveillance, including a spare, and there was a pave-pause radars that were installed in the 1980s along the U.S. coast, and they were able to detect a sea-launched ballistic missile launch, giving about 13 to 14 minutes warning time to the U.S. president. U.S. presidents would have 3 to 4 minutes to take a decision for a launch option once information was received that these sea-launched ballistic missiles had launched. There are occasionally surprises. In 1998, a Russian Delta class launched a German telecommunication satellite with a Russian RSM-54 sea-launched ballistic missile without telling anyone. The U.S. immediately went on alert and then contacted the Soviets or the Russians at the time, and it became clear this is a commercial launch. Although it's very strange to launch a satellite for communications from a ballistic missile submarine. These are the BMUS sites that allow the U.S. to track missiles. You can see Grand Forks Air Force Base, which was originally where the missile defense system was located. You can see the Cobra Judy, which is the ship with a lot of surveillance equipment deployed in the Pacific. You can see Fylingdales in England. You can see Thule in Greenland. One of my students years later became an Air Force pilot and landed a Canadian Air Force aircraft at Thule. You can see the radar at Clear, Alaska, which looks into the Arctic. You can see the radar at Eglin Air Force Base that looks south over Cuba, and the Cobra Dane radar at Shemya Island in the Aleutians. You can see here the surveillance facilities in Canada, including the Dew Line to the very far north, which was eventually dismantled and replaced with another system. You can see the various air bases, for example, Bagotville, which had interceptors. You can see Cold Lake in Saskatchewan, which contained the Beaumark nuclear interceptors. This is the Thule BMUS site in Greenland. Also the Thule BMUS site, a single radar. These are Fylingdales in England. The U.S. Strategic Command, or U.S. STRATCOM. Its headquarters is at Offutt Air Force Base in Nebraska, and it controls the nuclear forces. You can see on the right a picture of when Bush visited Moscow. And next to him is a U.S. naval officer who is carrying the nuclear football. In other words, the U.S. briefcase that allows transmission of a nuclear launch. The authority to launch nuclear weapons in the U.S. is the responsibility of the U.S. President. Responsibility is normally accorded through the football, which is carried by the President's military aide. This system permits the U.S. President to transmit their authorization codes and to specify the strategic launch option selected. The National Security Agency, the NSA, then has the authorization to distribute the launch codes, which are stored at its command posts across the U.S. for ICBM, bomber, and submarine forces. The death of the President would lead to a reference to a succession list to other command authorities. There is a parallel organization to the NORAD. The NSA DIA Defense Special Missile and Astronautics Center, DEFSMAC, was established in 1964 to track all aircraft and missile launches in Ops 1 at the NSA headquarters. The customers for their information include the White House Situation Room, the National Military Command Center of the Pentagon, and the DIA Alert Center. This organization competes with NORAD for influence, and in some way is used by the U.S. because it's a system that is entirely controlled by the U.S., where NORAD is shared with Canada. The picture you can see here is the National Security Agency headquarters at Fort Meade, Maryland. Some of its contributions are: the Defense Intelligence Agency discovered in 1967 the Soviet FOBS system, the Fractional Orbital Bombardment System. The Soviets were testing the launch of satellites that were high speed, that could be replaced by nuclear warheads, that would go into orbit, but would circumvent American sensors by flying not over the Arctic, but by flying around the Antarctic and flying towards the US in the direction from South America. And they would do so in a very low altitude motion. 20 tests were done till 1971, and then the Soviets scrapped the operation due to cost. But possibly also because it was in violation of the Outer Space Treaty, which prohibited nuclear weapons in space, and possibly also because it was very destabilizing. The threat to put nuclear warheads orbiting in space is a problem because they're very difficult to detect, and they can be deorbited very quickly, since warheads fly or can fly at enormous speeds if they're in the low orbit. This is the command authority for missile launch as a part of the Presidential Succession Act of 1886. You've got the Vice President, the Speaker of the House, President pro tempore of the Senate, the Secretary of State, and so on. In the picture you can see the NORAD Ops Center. In 2002 I had the privilege of going to NORAD to visit their Ops Center in an exercise. They have 3 separate identical centers. The screens on the wall each represent information from a different agency, including the FAA, which tracks all aircraft in the US, and the US requires that all aircraft 1,000 nautical miles on both sides of the US identify themselves, and they track that information too. There's a seat there for the CIA, for the DIA, the Defense Intelligence Agency, for the various services. There's a Canadian military representative. It's a very interesting integrated system. We were shown a nuclear attack on North America, and what you see is oval or elliptically shaped circles around cities, because the missiles come in, the computers estimate a rough area around which the missiles are going to land, and as the missiles get closer, those ellipses and those circles shrink because the resolution increases, and it's possible with greater accuracy as time passes to guess where they're going to land. And so this organization doesn't launch missiles, but what they do is they send information about where the enemy missiles are coming in from and where they're going. Launch on warning, or launch under attack, LUA. To launch your missiles after the enemy has launched their missiles, but before they've impacted, is what militaries that have nuclear forces spend most of their time planning for. The BMUs in Clear Alaska and Thule, Greenland, and Fylingdale Moors in the UK would give only a 15 to 25 minute flight warning. The whole command process would take more than 15 minutes, so it was a very difficult process. Occasionally the US President is included in these military exercises. Here you can see a buried US launch control capsule under construction. These were built for all of the missile silos. So let's examine the timeline for a Soviet attack. So you can see in the horizontal axis from the left to the right, we have 0 to 30 minutes in 5-minute increments. So the first thing that happens is the Soviets launch their SLBMs from submarines in the Atlantic and the Pacific, and they launch ICBMs from the Soviet Union. Between 3 minutes and 6 minutes, you have an electromagnetic pulse burst, which then blinds a lot of the communications on the east and the west coasts of the US. Between 7 and 15 minutes, depending on how close the ballistic missile submarines got off the US coast, you have a series of detonations, hitting coastal targets like naval bases, the PAVE-PAWS radar that detects the flight of sea-launched ballistic missiles, and possibly Washington, D.C., which is not too far from the coast. Then you have, between 10 and 15 minutes later, attacks on air bases that are inland. Strategic Air Command. Even NORAD, headquarters at Cheyenne Mountain, could be hit. Between 27 and 35 minutes, the ICBMs arrive. Now the sensor system the U.S. has here is the U.S. detects with warning satellites within minutes. And they send out warnings to all the commands that the sea-launched ballistic missiles and the ICBMs are in flight. These are from satellites over the Soviet Union, the paved pause on the U.S. coast. So the coastal radars detect the incoming sea-launched ballistic missiles. Immediately the bombers and the tankers and the airborne command posts, the PAX fleet, which is the Air Force One, are launched. TACAMO is ordered. So all civilian aircraft are cleared from the skies. The NDS, which we'll talk about later, between 6 and 15 minutes detects detonations inside the U.S. The radars then detect the incoming ICBMs, the radars in North America, between 12 and 25 minutes. The last time to generate a launch under attack, LUA, is between 17 and 23 minutes. The last chance to safely launch an ICBM is between 25 and 27 minutes. And then the Soviets start detonating their ICBMs. So again, you can see here this broken down. In the top you have your impacts from the SLBMs and the ICBMs launched from the Soviet Union. In the second horizontal axis, you can see the sequence of detections by the US. The lowest horizontal axis is the detection and the decision-making process in the US. So you have the first detection, then you have low-level military leaders who confirm the operation. They then alert the senior leadership. This is within 10 minutes. The US president is then contacted. That's between 10 and 15 minutes. Recall, this is the time that Washington, D.C. has probably already been destroyed. So it's very likely the vice president or someone farther down the list of succession has been consulted. Then they prepare and transmit the emergency action message. This message is decoded by those that possess the nuclear weapons. And the launch sequence proceeds from 23 to 27 minutes. And the first missiles launch at 27 minutes. So 27 minutes from the moment of launch and first detection, and final launch of, or the first launch of nuclear missiles from the US. And all of this has to be drilled incredibly quickly. So US command architecture. In general, the US command architecture was much less centralized than that belonged to the Soviet Union, with US naval commanders being able to launch their own missiles without any codes until 1997, when permissive action links were imposed by the Clinton administration. The US had more redundant communications, but its safe command and control centers were less well integrated into the war-fighting network. Here you can see a buried US launch control capsule under construction. The US Secretary of Defense in the 1960s, Robert McNamara, created an airborne command network. He had a Boeing 707 EC-135s, of which there were 39. These were normally reconnaissance aircraft, refitted to also function as command aircraft. Between 1961 and 1991, some of these aircraft were kept aloft continuously, 24 hours a day. The President's plane, what we call Air Force One, which is the NAECP, the National Emergency Command Post, is always on a 15-minute launch notice. These were upgraded to the Boeing E-4B, the 747-2000, and were deployed at Offutt Air Force Base, Omaha, Nebraska, at the NAOC, the National Airborne Operations Center. There were 4 aircraft, so Air Force One is just one of the 4. Each of them is equipped with their own full battle staffs to command in time of nuclear war. Some of these aircraft could launch ICBMs by remote control to some unmanned silos. Some aircraft in the PAX, the Post-Attack Command and Control System, could also launch 10 Minuteman ICBMs at Whiteman Air Force Base, Missouri, that would send out signal codes to the bombers. This is similar to the Soviet perimeter system. The Navy had 20 EC-130 and 16 E-6A aircraft that were always flying, that could send out very low frequency communications from an 8-kilometer long cable to ballistic missile submarines. In the 1960s, the U.S. deployed the shielded communication ship, the United States Navy USS Northampton. Above, you can see the E-4B, which is the U.S. Air Force One, deployed at Offutt Air Force Base, Omaha. Below, you can see the Russian Ilyushin 80 C-3 command and control aircraft that is the equivalent of Air Force One for the Russian leadership. Nuclear war command centers in the U.S., which, as you saw earlier when we looked at budgeting, cost $25 billion since 1940, include the following. There is one, a $5.6 billion site that was spent at the NORAD Shine Mountains Ops Center. It's basically a bunker underneath a mountain. Shortly after construction, they discovered there was a fatal crack in the mountain, but because they had gone so far digging the bunker, they decided to continue. Inside, which I've seen, are large buildings on giant springs about half the size of a car. The buildings are 3-story buildings. The springs are enormous. The door is giant and metallic and is meant to absorb an enormous shock, but it's not facing directly outside. You have to go into a tunnel, and you can go out the other side of the tunnel. So any shockwave going down a tunnel would pop out the other side, and this door is in the wall. So this door would feel very little overpressure. I did take my Lovelace wheel when I visited, and I did some calculations, and the mountain is so thick, even if there's a crack in it, that you'd have to have an enormous weapon to create a crater big enough to dig down to the bunker. Number 2, $1 billion was spent on Site R, which is the Alternate National Military Command Center, the ANMCC. It's located at Raven Rock near Gettysburg, Pennsylvania. It's 10 kilometers north of Camp David, which is a camp for the U.S. President, which is frequently used for negotiations. There's a 500 permanent staff there, termed the Naval Administrative Unit, and it was even present in 1997. So this site is still operational. It's basically the equivalent of the underground Pentagon for the President. Number 3, High Point Special Facility, SF, Mount Weather, which is a bunker, and it's located in Berryville, Virginia. It's operated by FEMA, the Federal Emergency Management Agency. It's a continuity of government site, which means it has offices for many different agencies in the civil government so that U.S. can continue to govern itself after being attacked by nuclear weapons. At Mount Pony, which is at Culpeper, Virginia, is the Federal Reserve Board. Here you have banks of computers that contain copies of all of the banking information in the U.S., including electronic fund transfers. In other words, if there's a nuclear war and all the cities are blown up, all the banking information, all the mortgages, and all the credit card information is still stored at this facility. Number 5, the Green Beer or Casper site. This is a resort in White Sulphur Springs, West Virginia. It's designed as a bunker for the U.S. Congress. It's another continuity of government site. It was operational between 1962 and 1995. This is the site for the U.S. officials at Culpeper, Virginia. This is where you have all the banking information stored in computers underground. This is the U.S. Federal Bomb Shelter High Point Special Facility, Mount Weather, Virginia. This is where you have FEMA located, a continuity of government site. You can see at the white square the entry point into this bunker complex. A part of command and control of communications is the protection of one's own communications and the destruction of the enemy's communications. An important element of communications are satellites. Satellites are vital for early warning and communications. The US and USSR have both invested in destroying their opponent's satellites. Now today, of course, this is Cold War, it's shifted away. The People's Republic of China today has more satellites than Russia does. So they've been launching satellites furiously. In 1963, the US conducted a successful satellite interception operation codenamed Mudflap. On October 1997, a low-power 30-watt ASAT laser damaged an orbiting target satellite. The ASAT program in the U.S. cost $14.5 billion. The U.S. had two interceptor ASAT programs. Starting in 1963, Program 505 was deployed at Kwajalein Atoll in the Pacific, and it was able to launch a single Nike Hercules surface-to-air missile with a 400 kiloton warhead. This was replaced by Program 437, which comprised two Thor missiles with a 1.44 megaton warhead that operated from 1964 to 1970 on Johnson Island in the Pacific. Fear of an arms race led the U.S. to cancel the program. The U.S. did not want to provoke the Soviets into placing orbital nuclear bombs. So this was linked to the FOBS system, the Fractional Orbital Bombardment System, where the Soviets were practicing to fly low-orbit warheads around Antarctica towards the U.S. The U.S. operates the GODSS, the Ground-Based Electro-Optical Deep Space Surveillance System, which is located at Socorro in New Mexico, Maui in Hawaii, and Diego Garcia in the Chagos Archipelago in the Indian Ocean, a British possession. Anti-satellite capability. It was assumed in a general war that the Soviet Union would destroy the satellites of its opponents. In 1968, the USSR conducted its first satellite interception, and in 1979, its anti-satellite ground system became operational, and it was able to intercept targets out to between 250 to 1,000 kilometers distance. As you'll see later, this is very shallow. Most satellites are much deeper into space, and some of the satellites are tens of thousands of kilometers in space. So deep space satellite interception is actually, at the moment, still quite difficult. On October 10th, 1984, a Soviet Terra-3 high-energy laser facility at Sarishagan was used to track the U.S. space shuttle Challenger along with the Argun phased array radar, and this caused discomfort to the crew. The U.S. complained to the Soviet Union. China. On January 11th, 2007, China destroyed an 850-kilometer low Earth orbit satellite, moving at 7.42 kilometers a second, with a ground-based, hit-to-kill, two-stage solid-fueled ASAT, or anti-satellite rocket. On July 25, 2014, China conducted a second missile ASAT test. The U.S. response to the Chinese attack in 2007 was, on February 8, 2008, the U.S. struck a space satellite with a cruiser-based SM-3. A cruiser is a ship. An SF-3 is a very old, long-standing, standard missile, surface-to-air missile. So the U.S. used a ship in its naval arsenal to launch a missile into space to shoot down a satellite. The indicator here was, and it's been deployed now to all the other ships, this capability, is that most of the ships in the U.S. Navy can shoot down satellites, giving the U.S. Navy incredible power to isolate the battlefield. If they can deploy ships into a particular ocean, then the low Earth satellites, particularly those for surveillance, can be destroyed as they pass over the battlefield, making it difficult for the enemy to know and detect where the U.S. is, particularly detecting the U.S. aircraft carrier. So these are the orbit populations. You can see here the Molniya orbit. This is used for missile warning for the USSR, and it's basically elliptical. You can see here the semi-synchronous orbit. It doesn't stick over an area, but it sort of slowly moves over it. The US uses it for nuclear burst detection. So these would be the Vela satellites, that detected the Israeli detonation at Prince Edward Island near South Africa. The geosynchronous satellites are very far out. These are used for communications and missile warning, but only boost phase, because you can detect the fire coming out the bottom of a rocket as it launches. But once it's in space and the rocket has no longer using propellant, then it becomes very difficult to see them, and you need optical sensors that are much closer. Low Earth orbit. These are the satellites that are likely to get shot at. And they could be as distant as only 1,500 kilometers. Whereas for the geosynchronous orbits, you're looking at a distance of 36,000 kilometers, which makes them effectively uninterceptable. And the semi-synchronous, which are 20,000 kilometers, which are still uninterceptable. So low Earth orbit satellites include photo reconnaissance. You got to be close enough to operate the camera. Ocean surveillance, again, you're looking at ships at sea. Electronic surveillance, including radar. Communications, which basically take communications from one area to another area around the curvature of the Earth. This here is a satellite photograph of, yes, you guessed it, this is the Straits of Hormuz. Now, the U.S. has some countermeasures. The Milstar satellites, which are navigation satellites for the U.S. military, can evade damage by relocating from 37,490 kilometer orbit to a very deep 176,994 kilometer orbit. So it makes it almost invulnerable. During the Cold War in 1984, in low Earth orbit, the U.S. had 18 satellites and the Soviet Union had 55. Russia now has far fewer than that. In the Molniya orbit, the Soviets had 22 because they were the ones to use it. They would swing these satellites over the U.S. to watch the ICBM sites. The U.S. had only 3 in that location. The U.S. and the Soviet Union had 8 and 4 respective satellites in the semi-synchronous orbit, 24 U.S. and 13 Soviet in geosynchronous orbit. This is a satellite photograph of the straits around New York City. And the satellite here is a U.S. tracking and data relay satellite. Data relay is essentially a satellite that takes information from other satellites or from ground-based transmitters and moves them around the surface of the Earth. On the left is a Defense Support Program satellite. This satellite detects infrared, which means it focuses on looking at the plume of propellant that launches rockets into space. You can see on the top right a Navstar satellite. This is a navigation satellite. It allows U.S. Navy ships to know where they are. Doesn't always work. In the 1980s, late 1980s, a U.S. cruiser shot down an Iranian airliner from within Iranian waters. The part of the reason they shot down the airliner, killing several hundred Iranian passengers, is that the ship thought it was outside of Iranian waters and that it was being targeted by a military aircraft. A retransmission satellite is shown in the bottom right. This is the Soviet Mir-1 space station. It was mostly used for experiments, but you can imagine it could have been used as a base to interfere with U.S. satellites. On the left, we see a U.S. space shuttle in launch. On the right, we see the Soviet Buran, which could have been manned, but never was. It was launched into space, but it was operated remotely. Its purpose, like the space shuttle, was paramilitary. As I spoke earlier about Minister Marc Garneau, half of the missions by the U.S. space shuttle were military. This was the canceled U.S. X-20 Dinosaur space vehicle. And the U.S. has been working on these remote vehicles for decades. It's culminated in the U.S. X-37 robot space vehicle, which has conducted extensive missions and routinely spends months in space. At the time of this lecture, it's deployed on its 6th mission. This is the Soviet Buran recoverable space vehicle. This is the Buran landing. So here you can see on the right various altitudes of different satellites. And you can see it here characterized by where it is in the upper atmosphere. Iridium Communications Satellites was a company that provided sat phones, but ultimately those satellites failed. Global Star Communication Satellite, International Communications Satellite, Global Positioning System is out at 12,000 miles. Here you can see an ASAT rocket underneath an F-15. So the U.S. equipped its F-15 aircraft with the ability to shoot down low Earth orbit satellites. Here you can see an F-15 launching an ASAT in one of its tests. The Soviets have an equivalent with their MiG-31 interceptor, which is still in operation. On September 13th, 1985, this was the only jet aircraft ever to shoot down a satellite. The F-15 took off from Edwards Air Force Base. By the way, Edwards is a Canadian test pilot who died, and so the base was named after him. The F-15 climbed to 38,100 feet and vertically launched the anti-satellite missile at the Solwind P-78-1, a U.S. gamma-ray spectroscopy satellite orbiting at 345 miles. That's about 500 kilometers, which had been launched in 1979. This is the January 2007 People's Republic of China successful ASAT test. This here, the rocket itself, is an LM-3A missile that was launched from Sichuan province. This is the Israeli Arrow 3 missile interceptor that was adapted for an ASAT interception in a test launch on December 10th, 2015. This is the Cold War United States Navy observation ship Cobra Judy, equipped with phased array radars that would track Soviet missile tests. This is the Soviet space tracking ship Cosmonaut Yuri Gagarin that was very sadly used in a Hollywood B horror movie. This was the characteristic of the 1980s era ASAT systems used by the Soviets and the Americans. And they were both hit to kill and or fragmentation. Protracted nuclear war. So U.S. President Carter, in response to the Soviet invasion of Afghanistan, signed Presidential Directive 59 that called on the U.S. to develop and maintain the ability to fight a protracted nuclear war. It wasn't Ronald Reagan that thought about winning a nuclear war. It was Jimmy Carter. Limited nuclear war needed a shoot, look, shoot capability because it could last weeks. U.S. President Reagan continued the program in which government would survive for up to 6 months while fighting a protracted nuclear war, called Project 908, also known as the National Program Office, initiated in 1982, and it included a lot of pre-delegation to launch in time of nuclear war. The surveillance system it relied on was GWEN, the Ground-Based Emergency Network. It consisted of several hundred 91-meter remote low-frequency aerial towers that would report on the location of nuclear attacks. Here you can see a U.S. Air Force Strategic Air Command C-3EC-135P. So these were the reconnaissance aircraft mentioned earlier that were turned into nuclear command aircraft. Decapitation. The U.S. military took advantage of Soviet shortcomings in command and control having to do with its reluctance to decentralize authority because of its mistrust of its own population. And so the U.S. prepared decapitation plans. However, there was not universal support. Eisenhower, on the option of a preemptive nuclear attack option on the USSR in 1954, said, quote, "No matter how well prepared we may be, no matter how certain we are that within 24 hours we would destroy Kuibyshev and Moscow and Leningrad and Baku and all the other places that would allow the Soviets to carry on war, I want you to carry this question home with you. Gain such a victory, and what do you do with it? Here would be a great area from the Elbe to Vladivostok and down through Southeast Asia, torn up and destroyed without government, without its communications, just an area of starvation and disaster. I ask you, what would the civilized world do about it? I repeat, there is no victory in any war except through our imagination, through our dedication, and through our hard work to avoid it." Close quote. So, war termination. Command and control is required to end a war because you need someone to negotiate with. So there's a consequence when you decapitate an opponent. Nevertheless, the U.S. proceeded with decapitation technologies. They developed 50 B-61-7 deep penetration bombs that were converted in 1990 into B-61-11, and they could penetrate up to 3 to 6 meters of hardened cement before detonating. They were built into a depleted uranium casing and deployed since 1997 from B-2A bombers. The Cold War Command NATO structure. Current NATO structure reflects the absence of an immediate threat, but during the Cold War you had the following commands. The North Atlantic Council, which was the highest political authority for consultation, delegated military policy to the Defense Planning Committee. The Military Committee, consisting of the delegates of the chiefs of staffs of every member country, would conduct the war, including the launch of nuclear weapons. Subordinate to them are three regional commands. Allied Command Channel, Allied Command Atlantic, likely to use anti-submarine warfare nuclear weapons, and Allied Command Europe, responsible for using battlefield tactical nuclear weapons. You can see on the left the NATO communication satellite 3B. Now what we have on the right is the chain of command for the release of battlefield nuclear weapons. So you will have a delivery unit, possibly an artillery unit, and they're going to ask permission. This would go to division artillery, to division headquarters, to corps headquarters, to CENTAG, the Central Army Group. This would then go to Allied Forces Central Europe, which would go up through SACEUR, which is the Supreme Allied Commander in Europe, the head of NATO. This would then go to the NATO Military Committee. It would go to the U.S. National Command Authorities, which would be the U.S. President. There might be a reference to political allies as to whether you should launch a nuclear weapon. The authority would then go down to the U.S. SACEUR, down to the Commander-in-Chief of U.S. Army Europe, down to the U.S. Custodial Unit, and then order would be given to launch. Now this is probably the pattern of command for the initial request to use nuclear weapons, but with pre-delegation, you're probably looking at the Commander-in-Chief being given authority, and he may even delegate to particular units to continue operations. So you can see how long this could take in terms of hours, not minutes, hours, which is why pre-delegation would eventually likely be adopted. So you're looking probably at a 24-hour decision for the launch of a first nuclear weapon because of its sensitivity and because it's highly escalatory. The military, of course, would like all nuclear weapons pre-delegated at the tactical level so that military commanders could launch nuclear artillery anytime they wanted to, as if it was conventional. But there's a clear political implication, possibly, or possibly not. It's very difficult to say. So what are some of the command issues? Well, because of the fear of escalation, political leaders will want to control the use of nuclear weapons. This picture is of the U.S. Fairchild Air Force Base in Washington State. This Air Force Base is responsible for global weather surveillance. Number 2. But once nuclear war has been initiated, failure to delegate will permit the opponent a considerable advantage in decision-making speed. Military leaders will therefore press for a general release order, perhaps with a delegated civilian to set the rules of engagement and to provide on-site approval of missile attacks. The 1986 Goldwater-Nichols U.S. Department of Defense Reorganization Act basically streamlined this command process. The chain of command for theater and tactical nuclear weapons at sea and on land was basically altered and simplified to the President, to the Secretary of Defense, to the combat commanders in the field. So it was abbreviated significantly. Below you can see a picture of a U.S. Air Force RC-135 strategic reconnaissance aircraft. Number 3. NATO's policy of first use would likely fail because the cumbersome command structure would lead it to Soviet interception and possibly trigger a Soviet preemptive attack. There was the case of the Soviets, who were monitoring communications and who are invited as advisors on NATO exercises, largely to reassure them that NATO is not about to invade the Soviet Union, that during the 1976 NATO Reforger exercise, in which Americans would fly into Germany and re-equip their equipment and drive to the front, that permission to go nuclear by the political authorities had been given 2 hours prior to the soldiers receiving it. Why the Soviets would reveal this is astounding and arrogant, and it shows that they were using their intelligence and showing it off and probably undermining it. The picture is U.S. Ellsworth Air Force Base Missile Launch Center. Number 4. Because of the decentralization of nuclear warheads to their respective national forces on the opening of hostilities, in order to preserve them through dispersal, there would be a serious coordination problem. If German forces were to be hit by a nuclear strike, they would chain gang the other NATO members into nuclear use, despite the absence of a traditional NATO requirement for policy consensus. Below is just a field headquarters. 5. There's also the issue of coordinating national missile forces, such as those of the UK, the US, or France, and tactical weapons deployed with such states as Turkey or Italy. If the Soviets hit the UK, the British may be compelled to strike the Soviet Union with strategic forces, thereby chain-ganging the rest of NATO into a strategic nuclear exchange. Here is the control room of a British Polaris ballistic missile submarine. Here you have the costs of targeting and controlling the bomb. It cost $831 billion. Strategic command and control was $182 billion. Intelligence was an astounding $500 billion, but included satellites as well as spies and other issues. Continuity of government bunkers were $10.8 billion, and the space shuttle and space support was $26 billion, although the cost was probably shared with NASA. There was $2.4 billion spent on nuclear war planning. Meteorological program was $5.4 billion, but it included satellites. Mapping was $9.5 billion. This was a big deal because the US, when it deployed its ballistic missile submarines, because ballistic missile submarines have no windows and can't use active sonar, otherwise they'd be detected, the US needed the entire map of the ocean. This is currently being conducted by the Chinese and the Americans in the South China Sea with drones, and the Chinese and Americans are harassing each other. Overhead costs, which is basically paying for buildings and janitors, cost $95 billion. So imagine a situation in the developing world where you've got terrestrial countries sharing a common border, like India, Pakistan, or India and China, or China and Russia. It takes 300 seconds for a Pakistani missile launched from within Pakistan to hit New Delhi. That is 5 minutes. So the decision time is significantly abbreviated. We're not entirely sure what the command authority is in India. We assume it's the Prime Minister, and then the Prime Minister would have to talk to their political council and then would have to transmit to the equivalent of the military chiefs a response to whatever Pakistan did. Pakistan faces the same issue. In Pakistan, the president controls the nuclear arsenal, although it varies depending on who's in charge, because sometimes the Prime Minister is more influential. And then you have a very strong military headquarters in Pakistan that can then delegate the weapons. Below, there's a picture of a Chinese IRBM being relocated at a site.